All right, everyone, this video is for section 7.4, partial fraction decomposition, also known as partial fractions. The textbook gives a pretty good motivation for this, okay? This is gonna be a tool we use, just as a little preface. This is gonna be a tool we use when we have an integral of like a fraction of polynomials. So when I have like an integral like where I have one polynomial over another, and I can't solve it using a nice U substitution or something like that. Okay, so that's the idea. Now let's look at this example from the textbook, in the first couple lines of the textbook. So let's consider this expression here, okay, this 2 over x minus 1 minus 1 over x plus 2. I can find a common denominator and make this into one fraction. Okay, and if I do that, I get this term here. Okay, if you are unclear of that, try combining this fraction on your own, and you should arrive at this thing. Okay. Now, let's try and integrate this. Okay, if I try and integrate that by itself, it's pretty hard. I don't have any tools I can use to do that. X plus 5 over x squared plus x minus 2. There's no good U substitution or anything like that I could do. Maybe I couldn't even really split it up. I couldn't even split up the terms. Okay, so this is hard to integrate. But we know that this thing is equal to this. Okay, so let's try and integrate this up here. Okay. So when I do that, the integral is really easy. 2 over x minus 1. Well, the integral of that is just 2 ln of x minus 1. And integral of 1 over x plus 2, that's just 1 ln of x plus 2, which is ln of x plus 2. All right, so I don't even need this 1 here. Okay. All right, so I see that this is my antiderivative. Okay. All right, it's the indefinite integral of this thing. And since these two are equal, okay, this is the integral of this as well. Okay. So that's the idea. This is maybe the motivation is clear now of why we want to be able to do this. We want to be able to take a hard integral like, I have a polynomial divided by a polynomial, maybe it's a hard integral, and I want to split it up into easier chunks, okay, where maybe it's still a polynomial over polynomial, but it's been split up into a couple chunks that are easy to integrate, okay? And if we think about it, that's what's really going on here, right? I have this hard integral, and I just know from my previous work that, well, this hard integral is equal to these chunks of easy integrals, okay? So the integral of this is equal to the integral of this, which I can find easily. Okay, so that's the idea of what partial fractions is doing. We're splitting up hard fractions of polynomials into easy fractions of polynomials. Okay, easy chunks. And partial fraction decomposition is going to be the tool we use to do this. There is some depth here, okay? If I have, for instance, let's say I have a polynomial over polynomial, and even if I factor the bottom, let's say I have like x over x plus 1 times x plus 2, okay, dx. What does this equal, okay? Well, it's going to be x plus 1 plus x plus 2, something like this, but the question is, what are the tops of these fractions, okay? It's not as easy as just, so an example of what we can't do is like if we have, okay, if we had something like this, this does not equal, we got to be careful how we split it up. We can't say it's equal to this. Okay. Okay, so hopefully that's clear. We got to be careful how we split up these fractions. Okay, so partial fractions is going to be the method we use to do this. Okay. There is a requirement to use this partial fractions method, and we require that the degree of the top is smaller than the degree of the bottom. So degree of numerator smaller than degree of denominator. What do I mean by degree? I mean the largest power of x, right? So if I had x cubed plus 4x squared plus 7x, blah, 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 x to the 5 plus 6x minus 3. Okay, what's the degree of the top? Degree of top is 3. The degree of the bottom is 5. Okay, so I'm talking about the largest power of x. Even if this was, 4x to the 5th, something like that, that doesn't affect the degree of the denominator, right? The largest power of x is still x to the 5th, so the largest power in the degree of the denominator is still 5. Okay. So that is our first requirement. We require the degree of the top to be smaller than the degree of the bottom to use this method. What if that's not the case? Well, we don't just give up. If the degree of the top is greater than or equal to the degree of the bottom, we can play around with it and fix that situation by doing polynomial long division. So, and that actually might be the only thing we need to do to make this into something we can integrate. So let's look at this example. X cubed plus x over x minus 1. I'm trying to integrate that. Okay. Well, the degree of top is bigger than the degree of the bottom, so I'm going to do polynomial long division. Okay. Let's see what happens when I do that. And if I'm going to go quickly through this long division, and then in the problem video, I'll review more in depth how to do polynomial long division. Okay, so if you need a refresher on polynomial long division, check out the problem video I'll post later. A word of warning, some of you might prefer the synthetic division thing that is usually written like, what is it? If I was going to do this by synthetic division, it would be like, it would be set up like 1, 0, 1, 0, something like that. And I have 1 over here. And you do this weird method of finding the answer. I would not do that in this section because it's not always going to work. So synthetic division only works when this thing we're dividing by is a monomial. Okay, so it is in this case, meaning the thing we're dividing by is something simple like x minus 1 or x plus 2. Okay, it's not going to work for other divisors. Okay, so polynomial long division, this method, this should always work. So this is the safer bet. Okay, so I'm going to do polynomial long division. Just a quick note, I guess. Polynomial long division is all about matching this term to this term. Okay, so what do I need to multiply x by to get to match x cubed? I would need to multiply that by x squared. Okay. And if you want, you can put like, you can fill in the gaps here. Okay. All right, so I need to multiply this by x squared. Subtracting. All right, now what do I need to multiply x by to get x squared? X. All right, and then what do I need to multiply x by to match 2x? 2. Okay, and then I don't have anything else to bring down, so my remainder would be minus 2, and then I'm going to write that as minus 2 over x minus 1. So after I do polynomial long division, I get this. X cubed plus x over x minus 1 is equal to x squared plus x plus 2 minus 2 over x minus 1. All right? Now, let's replace this in our integral with the result of our division. Okay? So the integral of x cubed plus x over x minus 1 dx is equal to this integral. Now, the good thing about this right side is that everything here is easy to integrate, right? I can integrate x squared, x, 2, and then what is this integral? Well, that's just going to be an ln integral. It's going to be 2 ln of x minus 1. So that I know the antiderivative of all this stuff. It's all right, so I'm done. So sometimes all I need to do is polynomial long division. Okay, so it worked out nicely in this case. In other times, this remainder is still going to be hard to integrate. Okay, so what happened in this case is that this remainder was easy to integrate. Sometimes that remainder is still going to be hard to integrate. All right. So in general, when we have the degree of the top is bigger than the degree of the bottom, we're going to do polynomial long division, and we're going to end up with a polynomial plus that remainder term, and maybe this remainder term is still hard to integrate. Okay, now the degree of the top will definitely be smaller than the degree of the bottom. So now we'll be able to use the partial fractions method. But again, maybe it'll be a case like this where we're done after the division step. We don't have to go any further. Okay. And again, this is just something we do when the degree of top is bigger than the degree of bottom. Okay. All right. So if that's not the case, if the degree of top is less than the degree of bottom, okay, then we don't even have to do that division step. We skip right to the partial fractions. Okay. So I'll kind of write out the steps for this partial fraction, this section as we go. Okay, and then I'll kind of collect them all at the end. So step one is to make sure that when we're working with our fraction, our polynomial over polynomial, we need to make sure that the degree of the top is less than the degree of the bottom. And if it's not, our first step would be to do a polynomial long division. Okay. All right. So now let's focus on, let's assume we have something Rx over Qx. These are both polynomials, and degree of R is less than degree of Q. Okay, so that's what all the remaining steps are going to be about. Okay, we would want to factor Q, that denominator, as much as possible, factor it completely. And we're going to get 4 cases depending on what that denominator factors into. Okay, so we got to be able to factor it, and we're going to get 4 cases depending on those factors. So we'll start with case 1, and then once we figure out how to do case 1 completely, cases 2, 3, and 4 are pretty straightforward. Okay. So case 1, the denominator factor is the denominator is the product of distinct linear factors, meaning we can factor that denominator completely, and when we factor it, there's not going to be any repeats or powers. Okay, so what do I mean by that? Let's say I have Rx and I have x minus 1. Well, let's consider this. Let's say I have Rx over x squared minus 1. Well, then my step 2 would be to factor that denominator. Okay, what does that factor into? X squared minus 1 is, we can factor that into x minus 1 x plus 1. Okay. So distinct linear factors, what does that mean? It means both of these things are linear, meaning the largest power of x is 1, right? Power here is 1, power here is 1. So I don't have any factors like x squared plus 3. Okay. Boom. So I don't have anything like that. So the largest power of my factors is 1, okay? And I don't have any repeats, meaning I don't have like, I do not have x minus 1, x plus 3, x minus 1, okay? So notice in this how I have x minus 1 twice, okay? So I don't want that, okay? Another way to write this, okay, is this case is the same as this, right? Okay, so I don't want any powers here in my of my factors. So I don't want either of these cases. All right. So what do I want? Again, I want distinct linear factors. So all of these things are linear, and none of them are the same. Okay. It doesn't matter if there's a coefficient here or if that's some constant. Okay. As long as they're linear and no repeats / powers. Okay, so that's case 1. All right. Now I want to, so after I factor, I should get a bunch of distinct factors here, no repeats, no powers. Okay, let's just work with 2 factors for now. Okay, this might factor into a bunch of them. Maybe there's like 4 or 5 factors. Okay, maybe it goes on for a while, but let's just work with the case where there's 2. Okay, it'll be clear what happens when there's more factors. All right. So I factored the denominator and I get a bunch of factors like this. Okay, I leave my numerator like it is. And then on the right side, and this is kind of step 3, I will be able to write this as this right side. Okay, so I know I'll be able to write this fraction as a over the first factor plus b over the second factor. Okay, and the order doesn't really matter. Okay, it doesn't matter which order we write these in. I will be able to write it as a over a1x plus b1 plus b over a2x plus b2. So I want to be able to split it up by factor. Now, what are these capital A and capital B? These are going to be constants, okay? And we're going to solve for these eventually, okay? So step 3 is what we've done here, okay? I've factored my denominator, and then I'm going to write my left side equal to this right side, where I have a constant over each of my factors. So a and b will be constant, and we're going to need to solve for these a and b. Okay, so just to rewrite what we have this left side. Okay, I factored my denominator and I've written it as this right side. Okay, where in these denominators I have one of each of the factors. Okay, now I need to solve for a and b, and I'm going to go through this step, and then I'm going to pause and kind of give you guys an example with some concrete numbers. So we need to solve for these constants in the numerator. How are we going to do that? The first thing I'm going to do is I'm going to multiply both sides by the denominator of the left side. Okay. So think, maybe write out on some paper what's going to happen when we multiply both sides of this equation by this denominator here. On the left side, the denominator is just going to cancel, right? I'm basically multiplying the left side by, okay. Okay. So I'm multiplying the left side by this. These factors are all going to cancel. Boom. And then I'm doing the same thing over here. And I'm multiplying here as well. Okay. So what's going to cancel over here? Okay. So try that on your own, and you should end up with this. On the left side, my denominator is going to get canceled completely. And on the right side, my denominators will cancel, but I'm going to have these parts left over being multiplied by my constants. Okay. And once I'm at this stage, I'll be able to solve for A and B in one of two ways. Okay, and that'll be step 5. All right. So before we go any further, let's give some numbers. Let's start an example and start working this before we get too bogged down in the steps. Okay, so let's start with this example. Let's go through the steps we have so far. So number 1, verify what degree of top smaller than degree of bottom. Boom, done. Step 2, factor the bottom completely. Okay. Well, how can I factor the bottom? I could try quadratic formula, or I could just try and eyeball it. So eyeballing it, I see this factors as x minus 3, x minus 2, right? Okay, so done. Step 3, split this up by factor. Okay, so this is a nice case 1, right? I got distinct linear factors, nothing repeats, no powers, etc. So I know that this is going to be equal to a over x minus 3 plus b over x minus 2 dx. Okay. And again, order doesn't matter. I could have just as easily written this as a over x minus 2 plus b over x minus 3. All right. So that doesn't matter. All right. Step 4, I need to start solving for my a and b. And I do that, let's just rewrite what we have so far. I need to multiply both sides by our denominators, right? Okay. I can actually forget about the integral right now. This partial fractions stuff, it's just a way to break up the fraction. It's got nothing to do with the integral. I mean, we're using it to integrate hard problems, but really it's about splitting up this fraction. So I can forget the integral sign for a bit. Okay, so I have this. My step 4, I believe it is. Yeah, we're on step 4, is to multiply both sides by this denominator, right? So on the left side, the denominator cancels completely. On the right side, I'm going to end up with a times x minus 2 plus b times x minus 3. Okay. Check this. If you don't see how to get from here to here, all right, start here and just multiply both sides and by the denominator here and see what cancels. Okay. So I've completed step 4 and I'm here. Okay. Boom. Step 5 is now to start solving for our constants a and b. All right. So now let's go back to our other file and see what step 5 says. Okay. So we want to solve for the constants, and we got 2 ways to do this. First way is to multiply out, okay? Multiply everything out on this right side. And then I'm going to group all my terms together by power of x. So like I want to get all my x squareds together, all my x's together, all my constants together. And then I'm basically going to match the coefficients on the left side to the coefficients on the right side, okay? And this is probably not making any sense to you guys, but let's go ahead and try and work through it, okay, in our example. So what did I say we were going to do? Let's multiply everything on the right side. Let's multiply it all out. So when I do that, I got ax minus 2a plus bx minus 3b, right? And now let's group all our x's together. Okay, so I got a plus b times x, right? Coming from here and here. And then I have, let's see, we'll group all my constants together. Okay. And now it's just about matching the left side to the right side. Okay. Over here on the left side, what do I have? Okay, I have 1x, right? So that means this a plus b has to equal 1. All right. And then what else do I have? I have minus 4, right? So this thing here has to equal minus 4. So I get this system of equations. All right. How can I solve system of equations? You might want to review this on your own. And again, I will, in the problem video, I'll go more in depth into how to solve these systems of equations. Basically what I do is I can add these vertically, right? So let's look at the a's. I have 1a here and negative 2a here. Okay. Well, let's see. Let's multiply this entire top equation by 2. Okay. If I did that, I would have 2a plus 2b equals 2. And now just add these equations vertically. Okay. If I add 2a to negative 2a, the a's are going to cancel. I see my, this should be minus 3, right? Because it's minus 3 here. All right. So if I add 2a to negative 2a, I get cancellation, right? Everything's going to cancel in that column. If I add 2b to negative 3b, I get negative b. If I add 2 to negative 4, I get negative 2. So negative b equals negative 2. In other words, b equals 2. All right. Once I have b equals 2, I can take that 2, that value of b, and plug it into either one of these equations. Okay. So let's plug it into the top one. I have 2a plus 2b equals 2. Well, b is equal to 2. So I got this. So I have 2a equals negative 2. So a equals negative 1. All right, so now I know my constants. Let's go back up to here. We said, I'll rewrite what we had. We had x minus 4 over x squared minus 5x plus 6. We had that's equal to a over x minus 3 plus b over x minus 2. And now I know what my a and b are. A is equal to negative 1, b is equal to 2. B is equal to positive 2. So my fraction has gone from this left side, and I've broken it up into these chunks now. I know it equals this right side. All right. So now if I was given the problem of integrating x minus 4 over x squared minus 5x plus 6, I know that's the same thing as integrating this right side. Okay. All right, so that's one way to solve for our a's and b's. All right, so what did we do? To reiterate, we were at the step for number 4. At step 4, we were here. I multiplied out everything on the right side. Okay. And that took me from here to here. Okay. And then I regroup everything by power of x. So I get all the powers of x together. So I grouped all my x's together. And then I grouped all my constants together. And then it's just matching the coefficients of the left side to the coefficients of the right side. Okay, so I had 1x here, so then this a plus b has to equal 1, because the coefficient here has to match the coefficient of x here, okay? And the constant here has to match the constant on the right side. So it's just kind of a matching game. And then I get a system of equations, and I solve my system of equations. All right. There's another way to do this. Okay, so let's go back to our step 4. What was our step 4? X minus 4 over x minus 3. Okay, so we're saying, let's clear our heads, and we're back at step 4. What's another way to solve this? Actually, step 4 is this, right? Okay, let's look at it. Let's go back to our original file and look at the other way to solve this. What did we say about the other way to solve this? Okay, so method 1 we just did. Okay, we multiply out the right side, regroup, match the constants. What's method 2? We just plug in values that are going to give us cancellations. Okay, so it sounds, it's a lot easier sounding, right? So let's see how it works. The problem with this way is it's not always going to work. This second method's not always going to work. Sometimes we have to use the first method. Okay. So what do I mean by plugging in values that give cancellations? Okay. Well, let's see what happens. Let's see, if I plug in 2 here, okay, if I plug in 2 for x, this term, this value is going to be 0, right? So this whole thing will get canceled out, all right? And then what am I going to be left with here? Okay, if I plug in 2 for x, I would have b times 2 minus 3. All right, so on the right side, I would have b times 2 minus 3, so b times negative 1. On the right side, I'd have negative b. What would I have on the left side if I plugged in x, 2 for x? I would have 2 minus 4, okay, so negative 2. Okay. So I would have negative 2 equals negative b. In other words, b equals 2. So really easy, right? Seems really easy. Again, the problem is this isn't always going to work. So that gives me b, and then once I have b, let's see, how can I find a? Okay, so again, we started here. All right, now I've solved for b. B is 2, so let's plug that in for b. And then let's see, if I plugged in 3 to both sides, what's going to happen? All right, this term would cancel completely, right? I'm going to have 0 there. Okay, if I plugged in 3 here, I have 3 minus 4 equals a, 3 minus 2. So I'd have negative 1 equals a times 1. In other words, a equals negative 1. Okay. So I've solved for my a and b again. So now I know x minus 4 over x minus 3, x minus 2 equals negative 1 over x minus 3 plus b over x minus 2. Yep, plus 2. Okay. So that's another way to solve for a and b. All right, what do I do once I've solved for a and b? All right, that kind of takes us through step 5. Now what do I do? The final step would just be to rewrite the integral in chunks. So split up my integral into chunks and then solve. Okay, so I now, from my partial fractions, my steps 1 through 5, I know how to take my hard fraction and split it up into my easier fractions. All right. Step 6 would just be to solve this right side. Okay, and at this stage, all our fractions should be easy to integrate. Okay, there are three types of integrals. I believe it's three that we need to know how to do. Once we get to this step, we're going to see all our integrals are going to have kind of three forms. Okay. So all our at step 6, all our integrals are going to have one of three basic forms, I believe. We're either going to have like constant over a linear term, something like this, okay? Or we're going to have, so I'll kind of keep it specific. Maybe we'll have 1 over x plus 5. Or maybe we'll have an x over x squared plus 3, okay? This we can solve with a u sub. Okay, so this type of integral we're going to be able to solve with a u sub. So we say u is equal to x squared plus 3, and then x would be 1/2 du, right? Okay, so this is going to be a u sub. And then we're also going to have integrals of the form where we have like a constant over a quadratic. So maybe we have like 1 over x squared plus 4. Okay, this is going to be like a tan inverse type integral. All right, so look at these three integrals, and if you can solve these three types of integrals, you shouldn't have any problem on step 6. I'll give you, so why do I call this a tan inverse type integral? Okay, let's look at this 1 over x squared plus 4 real quick. How would I solve that? If I had a 1 here, that's tan inverse, right? So what's giving me a problem is that I have a 4 here. Okay, let's divide out that 4. Okay, let's kind of bring it out here. Okay, these two things are equal, right? And I can bring that 1/4 outside the integral. And then this x squared over 4, I can write like this. Now do a u sub, u equals x over 2. And that should bring another constant outside. I won't go through all the way through this. And then it should basically transform this into a integral where we have like a constant c, and then we have 1 over u squared plus 1 du after this u sub. And then this will be tan inverse u times a constant, and then we undo our substitution and get like a constant times tan inverse of x over 2. Okay, so I would so from here see how that progresses. All right, so that's why I call this a tan inverse type integral up here. Okay, because after a u substitution, it's going to be a tan inverse integral. All right. So again, if you can do all these three types of integrals, you're going to be good on step 6, no matter what case we started with. Okay, so all of this was for case 1, but these three types of integrals are going to cover all our bases. For partial fractions decomposition, there's really no difference in the steps between indefinite integral and definite integral. So nothing changes if we have bounds, right? If there was bounds in any of these, it wouldn't matter. Or in our original problem, if there was bounds, it wouldn't matter. It's just at this step 6, instead of doing a indefinite integral with a plus c, we would do a definite integral and evaluate our bounds. So we don't have to do anything special for definite integrals. So remember, all these steps I've laid out are for case 1. Well, these steps work for any of our cases, but we talked about case 1, right? Where, okay, we factor in step 2, and when we factored, everything was linear and everything was distinct, meaning there were no repeats, no powers. So let's now start talking about the other cases. So we've covered all our steps, okay? So everything we've said still holds. These are all our steps. Now we're just going to cover the other cases, okay? Meaning when we factor the denominator in step 2, it's going to look different, and so we're going to do things slightly differently, but the same general steps apply. All right, so let's look at this case when I have 4x over x cubed minus x squared minus x plus 1. All right. This denominator looks nasty, but it factors nicely. Let's just look at the fraction. Let's ignore the integral for a second. Just look at the fraction. It factors nicely as x minus 1 times x minus 1 times x plus 1. Okay. All right. Now, what do I do? All right. So now I have repeated linear factors, right? So this is the same thing as I could have also written this as x minus 1 squared times x plus 1. So these are the same thing, right? So I have this repeated term, x minus 1, that might express itself like by having the same thing written twice or by having a power there, okay? It means the same exact thing. So what am I going to do? Instead of having a over x minus 1, okay, plus b over x minus 1 plus c. This is not correct, okay? So this is not correct. All right, so this is what we'd be tempted to do if we kind of follow the pattern of case 1, right? We'd have one constant over each factor, right? But that's not going to work because of this repeated term, okay? So how do I deal with that repeated term? What I'm going to do, I'm going to write a over x minus 1, excuse me. So that first one is still the same. And then I'm going to keep writing constants over that same denominator, and I'm going to increase the power of my denominator until I get to the number here, okay? So it becomes this, and then I would write the rest of my factors. All right, so compare with what I wrote above, which is wrong. Okay, I just have a single power of x minus 1 here, but actually it should be to the power 2. Okay. And let's see another quick example. Okay, let's say I had 7 over x minus, let's say x minus, to get a little variety, let's say x minus 4. And let's say it's to the power 3. Put 7x on top, and then I had x plus 2. Okay. So how would I do this? I have another repeated factor, right? I would do a over x minus 4, and then I'm going to keep increasing that power until I reach the number 3. Okay. So on the next term would be b over x minus 4 squared, and then plus c over x minus 4 cubed. Okay, and now I've reached the number 3, which matches the number here. Okay, now I am done with that factor. And then I would just do this last term here, plus d over x plus 2. Okay. So that's how we deal with repeated factors, okay? Repeated linear factors. Everything else about these problems is the same. I have the same process for solving for my constants a, b, c, etc. Okay. So let's continue with this one here. Okay. Let's continue with this problem. Okay. I factored it, and I got this stuff. Okay. Now let's pick up where we left off. Let's multiply both sides by this denominator here. What do I get? 4x equals a. And then do this multiplication on your own to see what we're going to get on the right side. Pause it as need be. I will continue writing right now. So on the right side, we would have a times x minus 1 times x plus 1, right? And then I'd have b times x plus 1 plus c x minus 1 squared. All right, so that's my right side. On the left side, I still just have 4x. The next step would just to be one of my two methods, okay? So you might be tempted to think that we could do that kind of method 2 for solving for our constants all the time, but that isn't necessarily going to work. Well, let's try it and let's see how far we can get with that method 2. So let's see. If I plug in x equals positive 1, what's going to happen? Well, everything, all this would cancel and all that would cancel. So if I plug in x equals 1, I would get, on the left side, I would have 4 times 1 equals, okay, this is going to cancel. I'd have b times 1 plus 1, so b times 2, and then that's it. So I'd have 4 equals 2b, so b equals 2. Okay. All right. What else, what other numbers could I plug in to get some cancellations? All right, I plugged in positive 1. What if I plug in negative 1? That should give me a 0 there, right? Okay, so if I plug in negative 1, on the left, I'm going to have 4 times negative 1. On the right, let's see. Oh, that's going to cancel. That should cancel. And I should have c times negative 2 squared. So I'd have negative 4 equals c times 4, right? In other words, negative 1 equals c. Okay, so now I got my b and I got my c. But now, let's see, there's nothing left. There's no other numbers to plug in to get cancellations, right? No other numbers I plug into these for x should give me zeros, okay? But at this step, we should have enough information to solve for a, okay? So this is a trick that can help us continue using that second method, all right? The trick is that this equality is going to hold no matter what x's I plug in, okay? Now I know what b and c are, and I'm looking for a, okay? So let's just pick a convenient number. At this stage, let's just pick a convenient number for x and see what happens. So let's pick like x equals 0, okay? If I pick x equals to 0, let's see what happens. So let's take x equals 0 and plug it into this equation, all right? On the left side, what am I going to get? I'm going to get 0. On the right side, I'll get a times, let's see, negative 1 times 1, so negative 1. I will plus b. I know b, we found b, right? b is equal to 2 plus 2 times 0 plus 1, so 1, plus, let's see, well, c is negative 1, so we can say minus 1 times negative 1 squared. So I have 0 equals negative a plus 2 minus 1. So 0 equals negative a plus 1. So negative 1 equals negative a, and so 1 equals a. All right, so a little trick to help us solve for these constants if we're using method 2. All right, so now let's kind of recap what we've said. We started with 4x, and we factored the bottom into x minus 1 squared times x plus 1. And we said that was equal to a over x minus 1 plus b over x minus 1 squared plus c over plus 1. And then we figured out what the a, b, and c are. They're equal to 1, 2, and what? Negative 1. All right, so now my hard integral breaks up into these easy chunks. Now I can integrate. All right. This is an ln integral. This is just a u sub, right? So I don't think I covered that in my 3 types of integrals, but it's fairly easy, right? And then this is just another ln type integral. So we get, let's see, ln x minus 1 plus what? Should be minus 2 x minus 1 to the negative 1 minus ln x plus 1. These two ln's we could combine into, let's see, ln of x minus 1 minus ln of x plus 1 we could rewrite using log rules as this if we wanted. This problem is coming from the book. This is part of example 4. So if you've noticed that and you thought, you know, I was getting something wrong, it's because of this. Okay. All right, so that covers case 2. So that's when we have repeated roots, you know, so when we have a power here, repeated terms, that's case 2. All right, now on to case 3. Case 3 is when we factor our denominator and we get a quadratic term that we can't break down anymore. Okay, so for example, let's say I had 7x over x cubed plus x squared. Okay, let's try and actually let's do x cubed plus x. Let's do x cubed plus x. All right. So let's say I'm trying to factor this thing. Okay, I'm trying to factor that denominator. Let's ignore the integral sign for a minute. Just think about the fraction. The denominator factors as x times x squared plus 1, right? The problem is I can't factor this anymore. Okay, if you try the quadratic formula on this, you'll see it gives, you know, if I try and do the quadratic formula on that, it gives you complex numbers. Okay, so this can't be factored anymore. So remember, another way to think about this is what is factoring? Factoring is going to be, let's say I'm factoring we did this one earlier, I believe. This, it factors in factors as x minus 3, x minus 2. And then I see if I plug in x equals 3, this equation is going to be equal to 0. And if I plug in x equals 2, this equation is going to be equal to 0. Okay. What about x squared plus 1? Okay. This is never equal to 0, right? Because no matter what number I plug into x squared, well, it's going to be positive, or, well, it's going to be greater than or equal to 0. And then I'm adding 1 to it. So I can never get back down to 0. Okay. So meaning I can't factor this anymore. Okay, so that's another way to look at this irreducible business. Okay, irreducible just means we can't factor it anymore. Okay, so we factor our denominator as much as possible, and we get this thing that we can't factor anymore. All right, so how do we deal with this? It's going to be the same. It's not the same, quite the same, but let's deal with everything else for a second. Okay, so the x term I handle the same way as my previous cases. I would do a over x. And then I'm going to have something over x squared plus 1. Okay, so I'm still putting this in a denominator. The question is, okay, now what do I put in the numerator? Instead of just having a constant, I'm going to have like a linear term here, bx plus c, okay, all in the same fraction. Okay, so let's rewrite this a bit neater. Okay, so I have a over x plus bx plus c over x squared plus 1. All right. And then the rest is the same. The rest of the steps are the same. I would multiply both sides by this denominator, and then my steps for solving my constants are the exact same. Okay. So let's see a quick example of this. Let's go to another example from the book. Let's say I have 2x squared minus x plus 4 over x cubed plus 4x. Okay. All right, denominator of tops, less than denominator of bottom. So step 1, check. Step 2, factoring my denominator, right? Okay. Boom. So 2x squared minus x. Let's forget about the integral sign till the end. It's 4. I factor the denominator, and just like the previous case, I pull out an x. Then I got x squared plus 4. Okay, so this is another one of those irreducible things. 3. Let's split up by denominator. Okay, this is case 3. So okay, just rewriting. And then splitting up by denominator, we have a over x. Okay, that doesn't change. And then, as I stated just a moment ago, we would have bx plus c over x squared plus 4. Right? Step 4, multiply by my denominator over here. Okay, so I would end up with 2x squared minus x plus 4. Okay, equals, try and do this on your own, and you should see it equals a times x squared plus 4 plus bx plus c times x. Okay. Now I need to solve for my a, b. What have I got? Constants a, b, and c that I need to solve for. Okay. So now I can use one of my two methods. Let's try method 2 since that's easier, and maybe it'll work all the way, maybe it won't. Okay. So let's multiply everything out. I got ax squared plus 4a plus, see, bx squared plus cx. All right. Actually, this would be method 1, right? If I wanted to do the easier method, let's see, I'll plug stuff in. I'll try and plug stuff into here to get cancellations, right? Well, this might be a case where this easier method doesn't work, right? Because I can't plug anything into that to get a cancellation. Okay. If I plugged in 0 for x, let's see, on the left side, I would have 4. On the right side, I would have a times 4 plus 0. Okay. So I'd have 4a equals 4. So, okay, I get a equals 1. All right. Now I have a equals 1. Okay. But now, as I said, there's nothing I can plug into this to get a cancellation. So now, I know what A is, but I still don't know what B and C are. Okay. Let's see, are there easy values I could plug in? Let's try it. Let's try and plug in x equals 1 and see what happens. If I plug in x equals 1, I'll get, on the left side, I would get 5. On the right side, I would get 5 plus b plus c times 1, right? So now I have 5 equals 5, or 0 equals b plus c. Okay. So now I'm kind of stuck, right? Like if I keep plugging in stuff, I'm just going to get more systems like this. So this would be an example where I can't do that easy plug-in method the whole time. So let's try our other method. Let's try our method 1. Okay. So let's kind of go back to the beginning and try that other method for solving for A, B, and C. All right, so what do I do? What is that other method? Okay, I'm going to rewrite my left side. On the right side, I'm going to multiply everything out. Okay, so I would get ax squared plus 4a. On the right side, or excuse me, and then I would also have bx squared plus cx. Now I'm going to regroup by powers of x. So I'm going to get all my x squareds together. See, so I have ax squared here. I got bx squared here. Okay, then I'm going to get all my x's together, plus cx, plus 4a. Okay, and then I'm just going to rewrite ax squared plus bx squared. I'm going to write that as a plus b x squared. And I got cx, then I got 4a. All right, equals my left side. And now let's just match the coefficients on left and right. Okay, that's all we're doing. So I have 2x squared over here and a plus b x squared over here. So a plus b has to equal 2. I have minus 1x here and plus cx here. So c has to equal negative 1. All right, I have 4 here and 4a here. So a, let's see, 4a has to equal 4. Okay. So I have this system of equations. And this gives me a lot of information already, right? 4a equals 4, so a equals 1. C equals negative 1. And then that's enough information to solve here, right? A plus b equals 2. Since a equals 1, b has to equal 1 as well. Okay, so easy system of equations. Okay, so I got my a, b, and c. Next step would just be to plug all that into my integral, okay, and solve. So, see, this was step 5, so step 6, just plugging all that in. Okay, so my original integral was 2x squared minus x plus 4 over x cubed plus 4x. All right, so now we know by finding our a, b, and c, it should be equal to this integral. Okay. The rest is just integrating, okay, and I'll show you one little trick for this part. Okay, this first thing's easy to integrate, right? 1 over x is ln of x. But what is the integral of this thing? That still looks pretty complicated. But this one, this second piece, let's split it up as 1x over x squared plus 4 minus 1 over x squared plus 4. Okay, there's nothing wrong with that. That's just splitting up. You know, I'm not breaking any rules by splitting it up like that. Okay. And now each of these should be easy to solve individually, okay? So this is an ln integral. This is an ln type, okay? This is a straight u substitution type. And then this is one of those tan inverse types I talked about earlier in the video. Okay. So if you can solve, let's say the hardest one out of these is this, right? The first two are just, let's see, ln of x plus 1/2 ln x squared plus 4. And then what's the integral of this thing? You know, it's minus the integral of 1 over x squared plus 4. Okay, so I'll walk you through this integral real quick. 1 over x squared plus 4. Let's just focus on this thing. I pull out that 1/4. I think this is the exact one I used as an example earlier. I do u equals x over 2. So du, 2du equals dx. Okay, so my integral becomes this. I pull out the 2, it becomes 1/2. I undo my u substitution. I get this. Okay, so the integral of this thing is 1/2 tan inverse x over 2. All right, so I just, I add that part. I cancel out that and replace it with this. I have a plus c, and so that's my solution. All right, last case, case 4. So case 4 is when I have repeated irreducible factors. So I'm not even going to write down integral. I'm just going to write down the fraction. Okay, so remember, partial fractions is all about dealing with the stuff inside the integral. Okay, let's say I have the case 1 minus x plus 2x squared minus x cubed over x, I'll go ahead and factor it, x squared plus 1 squared. So this is very similar to case 2, right? I have this irreducible thing, but then it's repeated, okay? So I deal with it in a similar way, okay? This is going to be equal to a over x, that's for this term. And then how do I deal with these repeated terms? I would have bx plus c over x squared plus 1. And I would keep writing factors like that until I got to the highest power on the left side. Okay, plus dx plus e over x squared plus 1 cubed. Okay, so that is how I would split this up. And then again, the rest of the steps are all the same. I would multiply this denominator to both sides, and I'd solve for my a, b, c, d, e. Okay, so that I think we can just set up. I'll do more examples in the problem video. But before I conclude, I want to have one little discussion. When I factor, some people have encountered this issue where, let's say I factor my denominator and it factors as x squared x plus 1. Okay. Well, this thing is just a linear term. Okay, so we know how to deal with that. But what about x squared? Okay, is this an irreducible quadratic, or is it a linear thing that's repeated, right? I could think of this as an irreducible quadratic, as an x squared, or I could think of it as x times x times x plus 1. I could think of it as that kind of, I could think of these individually as linear terms, and then it's a repeated linear case. Well, it should work out either way, to be honest. I think this way is a bit better because this x squared is technically, what is that? It's x minus 0 squared, right? So I think it's better to think of it as this repeated linear case. So I would set this up as, a over x plus b over x squared plus c over x plus 1, but it actually ends up being the same thing, right? Because these two, think about common denominator, these two could be combined as this, right? And so this is how I would have set it up if I viewed it as a irreducible quadratic, right? So it works out the same way, but I think I like this way a bit better. You could do it either way. I think that's my only caveat for this section. Again, more examples to come in the problem video.